So we have made the following transformation. Originally we had the following metric, which is, plus dt squared minus dx1 squared minus dx2 squared minus dx3 squared. And then we have made the transformation that t is rho hyperbolic sine of tau, and x1 is rho hyperbolic cosine of tau. Rho and tau are our new coordinates. After this transformation, we obtain the following metric, as we observed a few moments ago. Rho squared d tau squared minus d rho squared minus dx2 squared minus dx3 squared. The second and third coordinates were not touched during this coordinate transformation. So now we obtain a new metric tensor whose matrix G mu nu looks, it is diagonal and time independent as promised. It depends on spatial coordinates, it depends on rho, but doesn't depend on new time tau. So as we expected, we obtain a static metric. Static means that it is invariant under time translations, under the change of tau by tau plus a, and time reversal, tau minus tau. So as expected, due to the fact that we transformed to a homogeneously moving reference system, we have obtained a static metric. So let us describe let us first explain why this is a transformation to a non-inertial reference frame, and second, let us describe the properties of this metric. First of all, here we have to specify that rho is positive. We will see in a moment why. Then one can see that if one divides t by x1, one obtains that this is just hyperbolic tangents of tau, which means that constant tau are just straight lines passing through the origin, and as tau changing, when tau goes to minus infinity, this goes to minus 1. As tau goes to plus infinity, this goes to plus 1. So these are straight the constant tau lines are just straight lines passing through the origin in the coordinate system t and x1. And at the same time, one can see that x1 squared minus t squared is just rho squared, and the constant rho lines are just hyperbolas. So we have the following coordinate transformation. Originally, we had this lattice, coordinate lattice, t x1. Of course, we take a section of constant x2 and x3. So we just consider a section of constant x2 and x3. In this section, we had originally this lattice, coordinate lattice, rectangular coordinate lattice. And now we obtain a new coordinate lattice, which looks as follows. So we have this line in terms of original coordinates. Let me draw how it looks like. We have a line which corresponds to, this line corresponds to tau minus infinity. This line corresponds to tau plus infinity. These are lines of constant tau. Let me draw them by a different color. So these are tau constant. And the lines of constant rho are just hyperbolas. So these are rho lines of constant rho, rho constant. For rho positive and for rho negative, this is for rho constant and rho greater than 0. And for rho negative, we have also hyperbolas, but this corresponds to rho less than 0. So from rectangular coordinate lattice, we have obtained this kind of strange lattice, which covers only these parts of entire space-time. The reason for that is when rho is greater than 0, it is not hard to see that x1 is greater than modulus of t. As a result, for rho greater than 0, these coordinates cover only this quadrant of whole entire space-time. And for rho less than 0, these coordinates would cover this quadrant of entire space-time, for the reason that x1 would, in that case, will be less. Well, anyway, it doesn't matter. It doesn't matter. So it is important to stress that all of these hyperbolas for different rho have the same asymptotes, which are just these lines. And when rho becomes smaller, hyperbola becomes closer to the asymptote. And as rho goes to 0, hyperbolas degenerate to the two lines that x1 squared is equal to t squared, which is that x1 is equal to plus minus t, which are exactly the same lines. So these lines are corresponding simultaneously to tau minus infinity and rho equals to 0. Tau plus infinity and rho equals to 0. And intermediate values of tau are here, intermediate values of rho are here. So we have this kind of strange coordinate system. Now, one should notice that this metric does degenerate when rho is 0. When rho goes to 0, this element of the metric vanishes, and this is a degeneration of the metric. This degeneration is very similar to the standard degeneration of the two-dimensional metric in polar coordinates. If you have this metric, d phi squared, obviously it degenerates when r goes to 0. But this degeneration of the metric doesn't mean that the two-dimensional space where this metric is drawn has any peculiarity at r equals to 0. The space at r equals to 0 space itself is completely irregular. It's just the origin of the space. Similarly here, when rho goes to 0, the metric does degenerate, but the space itself, space-time itself, doesn't have any peculiarity along these light-like lines. This is the same original Minkowski flat space on these light-like lines. This is just degeneration of this metric. And now we are going to discuss the meaning of this degeneracy of the metric.